The network has problems classifying the data when the regression lines are curved. The problem is that the network as we created it cannot handle nonlinear data. We need to introduce nonlinearity by adding an extra layer. Where does the extra layer go? A network always has an input layer and an output layer. Our network already has these. Any additional layer comes in between. This diagram shows a network with one added layer. We call these added layers hidden layers. You know that the flower network has 2 inputs and 3 outputs. But why are there 4 neurons in the hidden layer? The answer is that the number of neurons in the hidden layer was chosen arbitrarily by me. We'll find out later whether this number is appropriate. Let me add the weights to the diagram. Notice there are now 2 weight matrices. One weight matrix from input to hidden, one weight matrix from hidden to output. The question is, what does the hidden layer do? Some explain hidden layers by saying it can pick up certain patterns in the data. Just like our brain picks up patterns from the overwhelming visual input it gets from our eyes. The human brain is a master at recognizing patterns like shapes, colors, and movement. When the brain sees a certain shape or a certain color, it does not need to analyze each pixel. It recognizes in an instant. It has to, or someone else will eat that banana. We want to achieve some kind of pattern recognition in our network too. That's why hidden layers are sometimes compared to the pattern recognition that happens in our brains. But since I am neither a brain surgeon nor an artificial intelligence expert, I cannot tell you if this comparison is accurate. All I can say is this. When data is nonlinear, hidden layers allow us to divide the data by curved lines. So how do we achieve a division by curved lines? Adding a hidden layer is not the whole story. Adding a hidden layer would just amplify activations from previous layers. The calculation would stay linear. We need to apply some nonlinearity to the hidden layer. You have already learned that activation functions add nonlinearity to a network. Which ones have you seen? Linear activation function, sigmoid activation function, and softmax activation function. Linear activation does not help us here. If the hidden layer would just perform a weight times inputs plus bias, it would just amplify previous activations but stay linear. We use the sigmoid for binary classification. This could be a candidate to create nonlinearity in the hidden layer. The softmax is used for multi-class classification and is not suitable for hidden layers. So, shall we choose the sigmoid? No. Although the sigmoid was very popular, it fell out of favor over the last years and it has something to do with its derivative. In this diagram you see the sigmoid function. This time I have added the derivative. The derivative is used to calculate the gradient. But as you can see, its value is very low when the input is either small or large. When a neuron is not activated correctly, it could be that the gradient to change this will never get a value to make a significant change to the weights and biases. This problem is called the vanishing gradient problem and gets more serious once we add more hidden layers. It turns out there is another activation function that is more suitable for hidden layers. It is called the rectified linear unit, ReLU in short. It has some advantages over the sigmoid activation function. This is what it looks like. Any input under 0 is cut off at 0. Any input above 0 is passed. To implement this function, we can use Python's max function. P is the prediction, and the output will be the activation. The function looks linear, but in fact is nonlinear. To update the weights, an activation function needs to be differentiable. The ReLU is technically not differentiable at input 0, but in reality this is not a problem. What does the ReLU derivative look like? The green line shows the derivative. Anything under 0 is 0, and anything above is 1. Simple enough, right? Here is the Python code to calculate the ReLU derivative. We have to change a lot. The good news is that once we are done, we have built a network that is so flexible that we can scale it up to recognize handwritten numbers with little extra effort. Let me show you the complete process of one epoch for a network with the hidden layer added. The feed forward will now have 4 steps. 1. Calculate the predictions of the hidden layer. 2. Apply the ReLU to activate the predictions. 3. Calculate the predictions of the third layer. 4. Apply the softmax to activate the predictions. The cost will be calculated. Then the error derivatives of the output layers are calculated. From the error derivative, the gradient is calculated. The gradient will have the desired changes to the weights from hidden to output, but the weights will not be updated yet. Notice that the weights matrix from hidden to output is called WHO. This is the name that will also be used in the code. Until here, everything works as before. But now a step is introduced that for a long time was very confusing to me. Well, I'll be honest, it is still confusing. Watch this. We know we need to calculate the gradient to change the WIH weights matrix. But to do that, we need to calculate the errors for the hidden layer. How do we do that? There is no target value to subtract here. Actually, this is the most complicated calculation in the whole network, and I'll show how it is done when we get there in the code. Once we have the error derivative, the WIH gradient can be calculated. I will use the name WIH also in the code. Finally, all the weights and biases in the network are updated. Sounds complicated? It is. Although it sounds logical enough, getting it all in your head is not a trivial task. The good news is that once we are done, the network will be so flexible that with minor changes, it will also be able to support recognizing handwritten digits. To move from a network with 2 layers to a network with 3 layers, we could change the existing code. But in fact, we need to change so many things that once again I will start with blank code. The only thing we will keep is the training and test data, the softmax function, and the log loss function. So here is the training and test data. The data is nonlinear and we need to create a neural network with a hidden layer. Let's switch to the neural network code. As you can see, it has the softmax function, log loss function, the epochs, and learning rate variable. This is the only code that we will reuse. The rest will be recreated. I'll start with the weights matrices. Just like before, I chose all values arbitrarily. I do the same for the biases. I create a training loop. Just out of curiosity, let's check the dimensions of Brad H. The predictions for the hidden layer is a matrix of 60 training samples by 4 neurons. Now I activate the hidden layer. You can already see the effect of the ReLU activation function. The first neuron's activations are 0. This happened because its predictions were negative and cut off at 0. If this happens to a certain neuron for all the training samples, we speak of a dead neuron. I will speak more of this in the next part. For now, I'm going to make sure all neurons have a value greater than 0. I will do so by increasing the bias for the first hidden neuron. All neurons seem to have a value over 0 now. Let's proceed with the prediction of the output layer. The predictions for the output layer are based on the activations of the hidden layer. Now I use the softmax activation function to activate the output layer. Let's see what Act O looks like. It is a list of 60 training samples and each row has 3 activations. 3 activations, 3 output neurons. And as you can see, the activations for each row sum up to 1. The feedforward is ready. Now I calculate the cost. The cost does not tell us much at this point. Let's start the backpropagation. The error derivatives of the output layer are calculated just like we did before. Now the error derivatives for the hidden layer need to be calculated. How do we calculate the errors for the hidden layer? We take the WHO weights matrix, transpose it, matrix multiply it by errors O derivatives, And finally, element-wise multiply it by the hidden layer predictions run through the ReLU derivative. The result is a 60 by 4 matrix. We now have the error derivatives for 4 hidden neurons for each training sample. So let's calculate the error derivative in the code, then calculate the WIH gradient, and finish the backpropagation by updating the weights and biases. I start by transposing the WHO weights matrix. And here is the calculation of the error derivatives for the hidden layer. Okay, now the error derivatives can be used to create the gradients. WHOD contains the deltas for the weights from hidden to output. BHOD contains the deltas for the output layer biases. Now I calculate the gradient for input to hidden. Now all the information to change the weights and biases of all layers is calculated. Let's combine the gradient with the learning rate and change all weights and biases. Done. You are looking at the code needed to train a neural network with 3 layers. Let me quickly test if everything works. I get no error messages. Now I will use the test data to test the network. I will calculate the predictions of the hidden layer. I activate the predictions with the ReLU activation function. I calculate the predictions of the output layer. I activate the predictions with the softmax activation function. Act O now contains the activation for 30 test samples. I go through the activations and compare them to the targets. Well, I'm curious how well we are doing. In an untrained network, the score is 33%. Let's increase the epochs to 1000. %. That is already better than the score without the hidden layer. But we can do better. %. Let's increase the learning rate. %. That is impressive. I bet we can optimize the parameters further to get a score of 100%. But I find it more interesting which test sample was not predicted correctly. Okay, we now know that test sample 21 was the bad prediction. The most active neuron suggests a purple flower. But in fact, the target shows that the flower is green. I looked up the bad prediction and it turns out that point 21 is this green flower. It's closer to the purple flowers than to the green flowers. I think we can forgive our network for making this mistake. And I can only repeat that a neural network is not a perfect function emulator. It is a function approximator. You always have to find a good balance between training effort and the result. With neural networks, usually good is good enough.